Okay, I started the recording, and the videos are available, as you know, in my YouTube channel. I posted a couple of days ago the last week video, so you can find them there. Before we start with the continuation of the last lecture, of the last topic I introduced last week, I just would like to make a brief comment on the floods that occurred recently in Tuscany. And, it has been once again an extreme event that caused the death of people and caused a lot of damages. And if you look at what happened, this is a suggestion that I give to you. We are discussing these events, and it is useful if you have a look at the videos. Now we have this opportunity, which we didn't have in the past, to look at the videos and see what happened besides reading the reports. And it is particularly interesting to see from your perspective how people were affected. So some people were drowned, some were injured, some had considerable losses also in economic terms, and losses of personal things. And I heard of a person who was crying because she said, I lost everything of my memories, of my pictures, because everything was kept at the ground floor, and they got 1 meter of water inside the house. Fortunately, they were not traumatically affected, physically affected, but they had a big loss. And this is something that we will discuss. So besides the injuries related to climate-caused event, there is the mental illness, the psychological trauma, which can cause mental disorder, because the shock is really important, and in particular when people experience lots of cultural heritage, maybe personal cultural heritage, personal memories, but also when a collective cultural heritage is lost, there are consequences in the long term. And if you see the reports, it may be useful. Of course, the question once again is, are these events caused by climate change or not? This is not directly interesting to us because it's not a medical question. Nevertheless, as I think I already mentioned to you, we cannot identify a unique cause for these events. When something of really extreme happens in terms of economic damage, or when a disaster happens, usually, in many cases, in most of the cases, there is a combination of causes. So there is a critical situation as a baseline, which is superimposed to a critical event. So very often we have several causes. It is very reductive to identify a dominant one. And so in this case, I'm not really sure how much climate change was influential in triggering this event. I don't have the data. I can speak for the Emilia-Romagna region, for the Romagna region, which was affected by a flood in May. In that case, it was undoubtedly an extreme event, no doubt on that. It was an extreme event. But it was also a problem of a critical baseline situation of the land and the river network. And I'm saying the land because you know that they have surveyed like 15,000 of landslides. So it is often a combination of causes, and the moral of the story, the message that I want to convey to you, is that when we discuss the effect of climate change and also the health effect of climate change, we have to try to get the picture clear of what are the causes. And very often is an interaction. And don't forget that when people are affected, it means that climate change is hitting society. So the societal system, and including the healthcare system, has a role in that. So if the societal system, we will see that today, is robust, even a very extreme event, even the climate change impact may be mitigated a lot. And very often the problem emerges when the the societal system, the society and the organization, the societal organization is not robust enough. So when we look also for, as I said, for the medical side of it, the medical side of the impact of climate change, it is very important that we try to identify what are the causes, because this helps us in better protecting people. Okay, so let's get back from the last lecture, and we started to analyze the climate change impact on health, and we stopped. Let me open the PowerPoint here. We started this figure here, by the way. And this is the figure, and I mentioned to you, I closed the last lecture showing to you this graph of the annual incidence of Lyme disease in the United States from 1991 to today, to 2018. And in particular, the vertical axis shows the incidence in terms of cases of Lyme disease per 100,000 people. And you see an increase, of course. And the increase is deemed to be caused, as I mentioned last time when I closed the lecture, by the increased temperature, which extends the life cycle of the ticks. And therefore, you know, if people are exposed for a longer time, it is more likely that they get the infection. On the other hand, there is to say here that there might be confounding factors which may have also caused an increase of the cases. I think you may be familiar with this term, the confounding factors. And here the confounding factor may be the increase in density of the wildlife that is host for the ticks. So this is also very important, because we know that the wildlife, because we activated protection programs and we are protecting it, it's actually increasing. And we also know that the equilibrium of these ecosystems has been compromised recently, because they also grow in number because of lack of predators. And this is why we are trying, for instance, to reintroduce wolves, because wolves are predators of the deers, which are hosts of the ticks. So this is a confounding factor. So actually, we have to be aware that these hosts are increased in number, and this may be also a cause of the growth of the Lyme disease. So even in this case, you can recognize two possible contribution. And of course, it's very important if we want to make, to activate, to plan programs for mitigating the risk, we need to know what is indeed the cause. It helps a lot. Okay, as I said, I concluded with this picture. And given that now we know that it's indeed important to know the baseline, so to know the situation of the systems that are interested by the health impacts of climate change, now it's appropriate that we discuss the state of the global health. So let me open the PowerPoint here because it is more helpful. Just let me get it. It's at the bottom of the lecture. PowerPoint presentation, perfect. And let me open. So state of the global health. I will focus on what is presented by IPCC AR5 report. Just 1 second, I get to it. Okay, here. The fourth assessment, actually. The fourth assessment of the IPCC presented a brief analysis of the state of the global health. What they presented is some statistics on the progress, the improvement in life expectancy during time. And here I am presenting in this slide some numbers, but I think it is more meaningful to look at this slide. It is life expectancy from birth. It's a statistic, of course, in years, and the progress from 1950 to current, to the present day. The vertical red dashed line is the present day, and also there is a projection that goes on up to 2100. These projections are simply derived by extrapolation. So it means that they get the rate of increase of the life expectancy in the past 5 years, and they assume that the same rate is preserved into the future, more or less. There are minimal corrections based on prediction of changes in the future of climate and other factors that may have an impact on life expectancy. But you see that the changes are really minimal. It's essentially an extrapolation. This is also what is done normally with the demographic analysis. Demographic analysis, in order to project into the future the rate of growth of the population, usually they extrapolate the recent trends. What is interesting here is to see the progress from 1950 to today, and you see that there has been a consistent increase. This is a global statistic. Actually, I don't really understand why there is this kind of step around 1960. Maybe also something that has been induced by outlier events. I'm not sure really, but I don't think it is interesting. What is interesting is to look at the general trend. The upper graph shows the increase in life expectancy, so the life expectancy, and the lower graph shows the annual change. So, as you see, there has been a consistent increase from 45 years to about 74 at the present day. This is a global statistics. And in particular, you can see that there has been a consistent increase from 2000 to 2015, 1995 to 2015. There has been a consistent increase of life expectancy. And then there has been more or less a stabilization, but still it's increasing. It is increasing with a lower pace, but it's still increasing. And what is the reason of this increase? The reason of this increase is the improvement in welfare, the improvement in the medicine, and the improvement in the health care system, of course. There are many reasons, but there is to say that this is a global statistic, and the situation is not homogeneous all over the world. Of course, in some countries it's increased more, and in other countries where these improvements that I just mentioned are less remarkable, in other countries the growth has been lower in pace. But still, I mean, this is something that is very important to consider. I want to show you a graph for Italy. So this is global. And by the way, here you see the source of this data. These are public data. Of course, what I'm showing to you is public. And you can make a selection for countries. So if you go there, let me just see if I can go there directly. Because I think it's interesting if I show you. Let me see if there is the way to go there. Cannot open. Okay, let me try with this solution. I go on the website directly because I think it is an interesting source of information. So let me just try here. Okay. Summary purpose, okay, accept all. And here you will see the graph. Okay, now it's coming. Okay, let's forget the advertisement. But anyway, what I should come, and what here you can search for country. So I put Italy. If you put the initials, you see that there are several suggestions. I put Italy, but you can make your own search, and you can download the data or save the image, and it's free. I don't really understand why now it's not showing up, but it should. Let me just try again. It should go, because it's not really protected. It is accessible. And anyway, let me show you the graph for Italy. Let's leave it there. Sorry? We can only see this. Yeah, because yeah, I understand why. Sorry, but you didn't lose anything because the graph didn't show up. So I understand. But anyway, if you want to try after, you can download on my website, and the link is reported on my web page, so you can try later if you're interested in a particular country. Now, this is Italy. And there is not a big difference. What is interesting to see is the vertical axis, the values, because Italy now is about reaching, it's above 86. It's close to, let me see, and you have to look at the current projection, is 84. This is the average age for Italy. At the global level, it was 79. So you may say that it's not a huge difference, but if you, I mean, we don't see the outliers here. There might be countries that have really a low life expectancy. Why I'm showing you this data? Because it's a baseline, as I said. So we have to take into account that life expectancy in general, health conditions are improving. When we predict, when we make predictions for the future of how climate change will affect human health, we have to consider this. We have to consider the fact that there is a negative impact given by climate change, other negative impacts that may be given by pollution, by several other causes, but in parallel there are improvements in the system, in the healthcare system, in medicine. There are improvements, and therefore it is not correct to make predictions only by accounting for the negative effects. Why I'm saying that? I'm saying this because we know that the development, our development has a cost, and it is also costly from the environmental point of view. So it's clear that the human activity is affecting the environment. The environment would evolve by itself much better without humans. On the other hand, we know that we have an impact, we know that we have to limit it. On the other hand, I was saying, we have to accept this impact in case the cost-benefit analysis is in our favor. So if increasing our life expectancy comes at a cost in terms of emissions, this is not always negative. Conversely, if reducing the emissions comes at a cost that means a reduction in impact on our welfare, this has to be considered, because this is the problem today. Today, we are, of course, concerned by the negative impact of climate change. So we are committed to reduce the emissions, we are committed to adaptation, but on the other hand, we have to consider what are the negative impact of adaptation and the negative impact of mitigation. And this is what we will discuss today. Because we have to always consider the two sides of the coin. So there is, as I said, a baseline in our life expectancies in the global state of health, which shows that overall the baseline is improving, and this is indeed important. Now, some numbers. The fifth assessment report of IPCC affirms with very high confidence we will discuss in a moment what high confidence means, that human health is affected by climate change. Of course, this is clear, and I would say that it's also well understood. The fifth assessment report was published in 2015. Now, as I mentioned to you last time, the sixth assessment report is being published. In the sixth, I had a look, by the way, at the reports that have been already published. There is no specific chapter for now on human health. So I refer to the fifth assessment report for starting this discussion. The impacts include the expansion of the geographical range of some diseases, of course, because the change in temperature, and also there are some diseases, as we will see, that are vector-borne, water-borne, very important ones, and these changes in the water cycle, in the temperature, of course, may expand the geographical range of some diseases. It may also be reduced, but overall, we are confident that it's expanding. And there are changes, as I just mentioned, in the distribution of some food, water, and vector-borne diseases, and with very high confidence. I think that you are already familiar with the terms waterborne, vector-borne diseases. Diseases may be spread by vectors, like for the case of the Lyme disease. Vectors are basically the hosts of the disease that come in connection, they come in contact with humans. So we use the term vector-borne to mean any disease that is conveyed by a vector. And the vector may be a living organism, or maybe also a matter like water. And in fact, a very significant part of vector-borne diseases are the water-borne diseases, the diseases that are conveyed by water. And also we define with food-borne disease the diseases that are conveyed by food. I think you are already familiar with these, and climate change has a very significant effect, in particular on the water-borne diseases, because of the direct connection between climate and the water cycle. So, the increasing future health risks are projected from injury, disease, and death due to light, for instance, and these are the most significant causes: heat waves and fires, so diseases caused by the fact that the temperature is increasing, and the heat waves, of course, with the increasing temperature, may become more intensive, more intense and more frequent. Fires, because forest fires are more likely to occur when we are in a warmer climate and when there is less rainfall. Given that climate change, after climate change, we predict that rainfall will be concentrated in extreme events, it means that dry periods are also longer. And when a dry period is extended, of course, the risk of fire increases. Undernutrition is another cause of health impact. Food and waterborne diseases, very high confidence, also in this case, and vector-borne diseases in general, medium confidence. And what they found is that climate change may be a multiplier. As I said, I mean, there is a baseline that is already critical, and the climate change may be a multiplier. So it is very important, and this is a question for you, it's a comment, a message for you. It is particularly important that you identify the situation where even a small impact, even a small change in climate may cause a great impact. So it's important to identify the situation where the impact of climate change is amplified by other critical conditions. This is extremely important. This is a topical research question. We should understand why there are some situations where even a big change in climate doesn't cause any problem, and situation where, instead, even a tiny change in climate or even an extreme event in the context of a stationary climate causes a big impact. And you can easily understand some cases in which this may occur, like, for instance, a poor civil protection organization, a poor healthcare system, or a situation where health is already compromised for other reasons. It's like the comorbidity that we learned to know during COVID-19. And also in this case, it's clear that if you have a climate change affecting a population that is already in poor health conditions, the impact may be amplified. And the key question is that we are able to quantify the amplification, because in order to design effective plans, we need to make a quantitative interpretation. A quantitative, if not prediction, at least projection, which means getting an understanding of the order of magnitude of what's going on. Yeah?
For example, when does a huge change in climate does not happen?
An example is, let me make a very stupid example. Let's suppose that you have an area with no population. Okay, so there is no impact, at least not on the humans, maybe an impact on the environment. Or let me make another example that is less stupid, but these stupid examples are very useful because I will get into a kind of a description of modeling in a few minutes, and that these examples are useful. Another example, I said, let's suppose that you have a big climate change, you have population exposed, but the civil protection, the healthcare system, they are very robust, so they can cope with it. Like, I have a flood, okay, but the population is prepared. I mentioned the fact that the ground level, people may lose many of their belongings. Okay, let's suppose that the population is experienced, know the risk, and they put all the belongings that have a value at the first floor or at an elevated position. So preparedness, or preparedness of people, preparedness of civil protection, preparedness of society. It's a different story because you have people exposed, you have the big climate change, but given that the system is robust, there is no impact. So you can identify three factors here: climate change, preparedness, let's call it vulnerability, okay, vulnerability, and the third factor is the presence of people, let's call it exposure. So if there are no people exposed, no problem. If people are exposed, but the system is not vulnerable because they are prepared, no problem. If you have no climate change, no problem. If you have even a tiny climate change, but people are not prepared, and there is a lot of exposure because people are living all of them on the ground floor, for instance, or they don't have air conditioning, then it's a problem. Okay, now, in this slide, I mentioned high confidence of the IPCC or medium confidence, low confidence. What does this mean? These are quantificators of uncertainty. I already mentioned to you, there is uncertainty when we deal with climate, like with the human body, there is uncertainty, of course. You know, when we make a diagnosis, there is uncertainty, fine. It is important that this uncertainty is quantified if we want to make a plan. So let's discuss how the IPCC, when dealing with climate change, when dealing with the impact, quantifies uncertainty. And this is, let's call it a box. If you look at my web page, it's here. So when you look at my web page, climate change impact on health, here it is. You see that this is inside a yellow box, okay? So this is a parenthesis. Okay. Now, how they quantify? You see that there is a table here, and the table is listing 9 cases of uncertainty measured in terms of 2 things, evidence and agreement. And uncertainty is called confidence here. When they have low agreement and limited evidence, they say low confidence. And the gray scale is indicating the confidence in this table. When they have high agreement, robust evidence, they say high confidence. What is evidence? It's clear. Evidence is data, is experience, is something that we can say it's objective. Because it's, as I said, it's maybe data, maybe clinical cases, maybe they are numbers. What is agreement? Agreement is the consensus of the people who are consulted in order to make this assessment. So, temperature is increasing. Temperature is projected to increase in the future, to continue to increase. Do all the consulted people agree with this projection? If they agree, then there is high agreement. And this contributes to increasing confidence. Now, let me make a consideration which I think it's much relevant. It's much relevant, and let me start with an example. You may know that when people are pooled with a question like, do you believe that humans are the main contributor of climate change? There has been a poll in the United States published a couple of days ago where they reported that for the first time less than 50% of the Americans reply yes. So there is about 50% of the population who is in doubt of the human contribution. On the other hand, if you browse the web a little bit, you will see that a much higher percentage of scientists are convinced that humans are contributing to climate change. And the reports vary in the range 97% of scientists, 99%. So these are statistics based on the consensus. Now, each consensus something that should be used to corroborate findings in science. It is questionable. It is questionable because science should be objective. Consensus is not objective. It is subjective. It's based on the consensus of people. So it is of course, it is subjective. You may remember very significant examples like Galileo, who was forced to apologize in front of the Pope because there was a consensus that his theories were wrong. And then 500 years later, I think it was Pope Johannes Paul II who apologized back. He recognized that the church at that time made a mistake. So, I mean, there were other cases in history, very important ones, where the majority of people was convinced that about a scientific theory, which turned out to be wrong afterwards. So we have to be a bit careful on that. So this way of quantifying uncertainty by the IPCC, which basically is adopted because they didn't find any other convenient solution, has some limitations. And when it's possible, you should look for an objective quantification of uncertainty. And you should look for numbers, not for qualitative assessment, which may involve a subjective component. Would you like I close the door? Maybe it's not there.
We're going to leave soon.
Okay. So let's wait. And so I'm sorry for that because I know you don't see the message. I got a message on Teams, which is a message by my university, but you didn't see it. So this is perfect. And so what does it mean? A more quantitative assessment of uncertainty. I will discuss this with you in a moment. With a more quantitative assessment, I mean a traditional way of estimating uncertainty in science, which uses the theory of probability. So basically, we shouldn't say high confidence, but we should say that we have a probability of 95% to be correct, which is not, it is a wrong statement, what I said, because probability doesn't, probability never states the probability to be correct, but it uses a more articulated language to say probability of not being correct. And because it is more objective, you know. Anyway, using probability is the alternative. And this is a relevant research question today. Like, how can we estimate our confidence in climate projection in quantitative terms through probability? This is an open question, but I just want you to be aware of the difference. When you see uncertainty quantified in terms of probability, or when you see uncertainty quantified in terms of a qualitative and a subjective assessment, you must be able to recognize it. Some people say that even probability is subjective, but I mean, there is a theory behind it. So there is something that is really well codified. And of course, everything can be subjective if you want, but when you have a consolidated theory behind it, it makes a difference. Yeah, thank you very much. Okay, now, after this premise, let's try to get into the details. How can we assess the impact of climate change on human Earth? What you see here is a graph that is similar to one that I showed you before, which shows the connection between climate and human Earth through the mediators, through mediating factors. This is a figure that is by the Environmental Protection Agency of the United States. So it's a figure that is different from the previous one that I've shown to you. And the previous ones were by the IPCC. But I think it is useful that you know different interpretations. First, we have the climate impacts. And as I mentioned to you last week, the most important ones are deemed to be increase the temperature. I'm looking at the orange rectangle on the top, climate impacts. Increasing temperature, precipitation extremes, which means rainfall, and extreme weather events in general. When one says extreme weather events, precipitation extremes are already included. But this is a description that probably wanted to emphasize the relevant role of precipitation. Actually, I think that also extreme wind is very relevant. And there are several risks of injuries related to extreme wind, and risks also for the buildings. But here is not explicitly mentioned. In some other classification, it is mentioned. And then the sea level rise. Sea level rise, keep in mind, I think I already discussed it with you. It's important for two reasons. First, they increase the risk of coastal flooding. Keep in mind that 60% of the human population lives in coastal areas. And in Italy, this percentage is probably higher. So what happens in coastal areas, and with coastal areas, we define the land areas between the coastline, between the sea, and an altitude in the land up to 100 meters. This is the coastal area, okay? And up to 100 kilometers. So if it is very flat, but it goes up, it goes beyond 100 kilometers, we don't consider it a coastal area. This means, for instance, that about half of the Padana plain is considered a coastal area. And in coastal areas, you may have an increased risk of flooding, but what is more subtle, because it's not so visible, is the saltwater intrusion. Saltwater intrusion means that you have an increase in concentration of salt, increase in salinity of groundwater. And if people drink that groundwater, okay, there are limits to salinity. So when the groundwater is controlled, basically you have to dismiss the well after a certain degree of salinity. But if it's not controlled, there is the risk that people drink salted water, and you know the effect of the increasing of drinking salt water on the human body. So there are several effects from high pressure to electrolytic imbalance in the blood, many other problems. So sea level rise is indeed a problem, and I think most of the problems are related to saltwater intrusion. Indeed, we found last year when the Po River was experiencing the most critical drought of the past 2 centuries, we monitored salt water going up the Po River for 50 kilometers. It's indeed a lot, and you understand why we consider a coastal area a land at a distance of up to 100 kilometers. Okay, so we have the climate impacts, and then they are mediated by 2 contexts: environment and institutional context, social and behavioral context. And in order to understand amplification, as I said before, it's important that you understand how these contexts work, how they function. So the environmental and the institutional context may be affected by land use change, ecosystem change, infrastructure condition. It's important because if you get a flood and you have the infrastructures that stop working, this is a huge problem. So the infrastructure condition can amplify the impact of climate change. Geography, agricultural production, and livestock use. And then you have the social and behavioral context, age and gender, race and ethnicity, poverty, housing and infrastructure, education, discrimination, access to care and community health infrastructure, pre-existing health conditions. And then there is the mediation of exposure. Exposure here is intended in a different way, and this is noted in my webpage, with respect to what I just mentioned to you before. I said exposure means that people are exposed. Here they interpret exposure as the factor that cause the damage to people. So here you see extreme heat, poor air quality, reduced food and water quality, changes in infectious agents, and the population displacement. And then you have an example of health outcomes. After all these mediations, what are the health outcomes that are mentioned here? Heat-related illness, cardiopulmonary illness, we will go into the details, food, water, and vector-borne disease, mental health. As I said, we will discuss these outcomes in detail, probably next week, because before discussing in detail the outcome, I want to discuss with you how we can assess the impact. So how, given a climate change, given a predefined climate change, what model we can use in order to quantify these health outcomes. Of course, it depends on the specific health problem, on the specific health outcome, but there is an underlying model, an underlying methodology that I want to discuss with you first. And so now we focus on the impact of climate change on human health. Okay. This is a more quantitative discussion, so there is also some very simple mathematics on it. I propose that we make the break before moving forward. If you don't mind, I will make the break 10 minutes, so I can leave at 6:15, because this helps me to save a lot of my time. Okay, See you in 10 minutes. I stop the recording. Okay, I forgot in my first part of the video, I forgot to share the screen, so you will listen my voice if you watch the video, but you will not see the slides. Now it's shared, as you see from the red rectangle. Let me minimize. I don't understand why we see this, and let me just 1 second. Let me see if the mouse goes on the screen. No? Okay, now. Okay, let's keep it there. I think it's not worth that we waste our time. Let's keep it there. It's not a big problem. Now, question for you. Did you get any introductory lecture courses on probability? You got it. Okay, good. During your first year, statistics, first year, maybe second year. Good. That's a good year.
And now we're not really.
Yeah, it's not.
And okay, how many credits were your introductory course on statistics? Do you remember?
5, 6.
5 or 6, yeah. So it was quite heavy, I mean. Yeah, okay. And you got an exam. Okay, good. Okay, so let's follow for estimating the impact of climate change, the guidance of the World Health Organization. I tried to look at many sources of information, and I found that this one, I think, is the one that I liked more. There is, as I told you, there is not an extended literature on climate change and health. So basically, I'm sure that there is a more extended literature on climate and health, but still, in my searches for information, I found that this one is the one that, in my opinion, gives the opportunity to give a real quantitative assessment. So what they say is that their purpose is to estimate the risk induced by a considered event. An event that is related to climate change in this case. So it may be the risk of flood, the risk of, and then we can estimate the risk, the increase in the risk of flood, or the risk of heat waves. Okay, so the risk is given by a combination of 3 factors according to these guidelines, which, by the way, I already mentioned to you. And it's a combination of hazard, and we will discuss in a moment what is, exposure and vulnerability. So what is the risk? First of all, let's define the risk as a measure of the expected damage during an assigned time period given by a considered event. Expected damage, what is the unit of measure? May be expressed in economic terms, but it may be expressed in other units. And in particular, keep in mind that some kind of impacts are intangible, meaning that you cannot monetize them. Even when you talk about the loss of lives, of course, we have insurances quantifying the economic equivalent of loss of a life, but you know that it is something that is very sensitive. So anyway, the concept is that R, the risk, is a measure of the expected damage. What is hazard? Hazard is the probability that a given event occurs in a given time period. So what is the probability of getting a flood during my lifetime? What is the probability of getting a flood every year? Perfect. And the time period is the same time period with respect to which you measure the risk. So if I consider as time period my lifetime, so what is the risk originated by floods in my lifetime? But if the period is 1 year, what is the risk of flood that is originated in 1 year? So hazard is the probability. Now, the adverse event can be completely disjointed by climate change, like earthquake, can be related to climate change, like landslides, tsunamis, cyclones, extreme temperatures, floods or droughts. The events can be also biological, like a disease outbreak, including human, animal, and plant epidemics and pandemics. The adverse event can be technological, like chemical and radiological agent, or explosion, transport and infrastructure failures, and can be the event societal, conflict, act of terrorism, migration, humanitarian emergencies. Okay, this is the probability, hazard is the probability that this adverse event occurs. Of course, we are mostly interested in the so-called natural events. Natural hazards include the events that are related to climate. They are called natural hazards to mean that they come from nature. But actually, some people are questioning now this terminology because they say that these events are no more natural but are caused by humans. So just keep in mind the sensitivity of the term natural when you talk of events that can be related to climate change. But in the scientific community, floods are still considered natural hazards. Maybe human-induced natural hazards, meaning with natural, as I said, that they are induced by nature. Okay. Now, vulnerability is the probability that the system gets damaged if the adverse event occurs. Okay, so probability, keep in mind, is adimensional, is dimensionless. Also vulnerability, given that it's defined as a probability, it's dimensionless. And I want to stress the concept. Vulnerability means that the event occurs and the system gets damaged. So what is the probability? Given that the event occurs, that the system gets damaged. So we take for granted that the event occurs, and then we estimate the probability. Of course, it depends, such probability, such vulnerability, on the state of the system, preparedness of population, healthcare system, whatever, related to the actions that we can put into place in order to avoid to be damaged by an adverse event. Exposure. Exposure is the value, not necessarily expressed in monetary terms, of the assets that are at risk, like people, buildings, environment, agricultural system, etc. I also include the environment, and this is another tricky issue, to measure in quantitative terms the damage to the environment. It is not easy because it's not easy to monetize it, because there are some damages that we may cause to the environment that are irreversible. Now, we take these three factors and we multiply them. So this is the fundamental equation of risk estimation according to this approach, which is suggested by the World Health Organization. This is what we use in engineering. And I was surprised to see that also the World Health Organization suggests to use it. In engineering, this equation is also used for estimating the risk of earthquakes. So what is the probability of getting an earthquake, for instance, in a year? What is the vulnerability? So the buildings are earthquake proof or not? And what is the exposure? What is the value of the buildings, the value of the people, the value of the physical injuries that people may suffer from? Now, about the units, about the use of monetary terms or not, there are some recent developments which suggest to separate the tangible risks, so the cases where the damage can be associated to a monetary value, and the cases where this is not possible. And of course, if you change the unit of measure of E here, of exposure, given that probability and vulnerability are dimensionless, you change also the unit of R in a way that anyway keeps the unit of R identical to the unit of E. So if you measure exposure in loss of lives, then also the risk is expressed as number of loss of lives in a year. Of course, you may have a high E, so a high number of people that would be killed, but if the probability, if the hazard is zero, you don't have any risk of losing lives in a year. And again, if vulnerability is zero, you don't have any risk associated to loss of lives. I think this is meaningful and interesting because it gives also the way to decompose a very difficult problem, risk estimation, in three simpler at least, problems. And this is a way of structuring a complex decision. This is a possible way of structuring a complex decision. Good. Now we have to estimate how, how we estimate P, V, and D, hazard, vulnerability, and exposure. So P is, as I said, the probability of getting an event. It is the factor that is associated to climate change mostly. Climate change is supposed to change the probability of getting an adverse event, to increase the probability. So estimation of P is a key step here. In my website, I included a box on probability. So you told me that you already had a course, so I skipped this. But I just want to remind you just a few concepts. First of all, how we define probability? Probability, we can define it in words, in a qualitative term by saying that it's the likelihood of an event occurring, which is fine. I mean. But in order to be very rigorous, we should define it in a more rigorous way, indeed. And the way that probability is usually defined is through the Kolmogorov's actions, which say that probability of an event is a real number greater than or equal to zero, fine, and the probability that at least one of all the possible outcomes of a process, such as rolling a die or tossing a coin, occurs is one. Let me be more clear. Probability is varying between 0 and 1. The first two axioms say that. I'm talking about just probability, and you have been also educated on probability density. Probability density is a further development, but probability, if you don't say anything more, is a number comprised between 0 and 1, dimensionless. And then there is the third axiom. I'm not interested a lot. If two events A and B are mutually exclusive, then the probability of either A or B occurring is the probability of A plus the probability of B. Probability, I like to teach it by referring to the most classical experiment, which is tossing a coin. Tossing a coin has only two possible outcomes. We assume that the coin cannot stand on its edge as an outcome. So we have only head or tail, and these two events are mutually exclusive. So we can say that the probability of head plus the probability of tail is 1. Because they are mutually exclusive, we can apply the third axiom. And another thing that I wanted to recall to you, we may compute probability, estimate probability in two main ways. The first one is through the frequentist estimation. I make an experiment and I count the number of outcomes, and I divide this number like toss a coin. I make an experiment, I toss the coin several times, I count the number of heads, and I divide the number of heads by the total number of tosses. This is, I compute the frequency, and I assume that the frequency of occurrence of an event, like the head, is an indicator, an estimator of its probability. And this is, I think, also the way in medicine you use it, you estimate it, by referring to a large number of patients and by estimating statistics on the outcome of a given therapy or a given treatment. But there is also another way to estimate it, is through Bayesian estimation. Bayesian estimation estimates probability based on your belief. So, for instance, there are cases like estimating the probability of the outcome from an election. You can't use the frequentist estimation because you cannot make an experiment by making the election many times. So basically what you do is you gain an idea, like I think the most favorite party is party A, and then you make like an exit poll, or you make a preliminary pool on a reduced sample, you integrate your preliminary belief, it is called prior belief, with rigorous approaches by applying the Bayes theorem. I'm not sure if you were taught on that. And with the additional information, and you gain a posterior estimation of probability, which is still based, influenced by your preliminary belief. Okay. So, how is climate change affecting probability? First, if we refer to a given adverse event, usually it's an extreme event. It's not like tossing a coin where the head is very frequent. It is an extreme event. So we have the problem of limited data, because extreme events occurs rarely, by definition. They are infrequent. It means that we don't have many floods to refer to. We don't have many hurricanes. Or if you think at, for instance, the bias storm, extreme wind, these are very rare. So we have this problem of lack of information. But usually, indeed, when dealing with these events, we try to estimate probability using the frequentist estimation. We observe river flow for 100 years, and then we count the number of floods, the number of times the people were inundated. And this is a way of estimating the probability of a flood. There is the problem of lack of data, so we try to integrate with our belief. So we adopt very frequently a Bayesian approach. But this is what we call historical estimation, using historical data, using experiment. What about climate change then? Climate change is supposed to have an influence on the probability, but how can we predict it? It is problematic because we cannot make an experiment. We cannot change climate or wait until climate changes and see what happens. So how can we estimate it? The way it is usually estimated, there are several ways, but the most popular way is by using climate models. Climate models, on the other hand, are uncertain, and it is a problem to estimate this uncertainty. And this is why the IPCC doesn't use a rigorous estimation of uncertainty, but uses something like high confidence. This is an open problem. And it is something that I really, I don't understand why. I'm still puzzled, because it's not considered a very urgent problem. It's a problem that is often dismissed. Like, okay, risk is estimated in this way, but how can I estimate the future probability of getting heat waves, of getting more thicks or whatever? And I think that the reason why it is a problem that is sometimes dismissed is that there is the belief by many scientists that communicating uncertainty to people undermines the trust of the public in science. I think this is the reason why many scientists refuse to talk about uncertainty. On the other hand, I also published recently some papers pointing out that we need a quantitative estimation of the probability of the future climate. And so we need to move from the IPCC definition, high confidence, to a probabilistic estimation. And I think there are ways of trying to manage this problem. And these are efforts that are ongoing. I am responsible for a project financed by the National Recovery Plan that aims at this. And in the project, there are some medical doctors, some researchers. They are experts in urban air pollution and impact on health. And we are working together. I'm trying to provide a quantification, a probabilistic assessment of the hazard in the future, which they can use in order to estimate the impact on health. Okay, probability is fine for us, so let's forget it. And you were also educated on probability density. I don't need to get deep into this. And the definition of probability density comes from the definition of probability. I think it is the most complicated thing to explain to students, to explain why, after defining probability, we need to introduce the probability density, which is a complication. It's a huge complication. And so I prefer to skip it here now, but I also think that it's a fascinating discussion, because indeed the probability density is introduced because we need to simplify the estimation of probability. Anyway, let's forget about it. This is just philosophy. And now, okay, but let's assume that hazard P can be estimated through a climate analysis, okay? So I need climate scenarios. Get familiar with this term. However they are obtained, climate scenarios and weather scenarios are future scenarios of climate and weather. You remember the difference between climate and weather. In order to identify the health impact, in some cases for some illnesses, it may suffice to estimate changes in climate. For other phenomena like floods, we need to get changes in weather. Okay, now let's talk about vulnerability. Vulnerability estimation requires an analysis of the social context, and in particular prevention policies, state of the healthcare system, age of people. And then you have to come out with a number. What is a number between 0 and 1 that quantifies the probability that the system is affected. There are, for some disciplines, like risk of flood, there are rigorous models for doing this kind of estimation, and also with reference to the social system, and in particular to the economy, there are rigorous models, and also for the health problems, there might be a rigorous model that analyze, for instance, what is the capacity of the hospital and compare it with the number of people that may be affected. There are models that can be used. We will see some details. And exposure estimation is based on economic or social analysis of the monetary or physical damage that may occur to population if an hazard materializes with an adverse event and people are fully vulnerable. So let's suppose that indeed the prevention system doesn't work, the event occurs, so what happens? What is the damage? Okay, now, so, as I said, we need to assess changing climatic variables, but be careful. If you read the first bullet point here, you understand that you have to refer to variables. And then it means that there is a first step here. You have to identify what is the variable of concern. It is temperature. Okay, fine. Is it risk of flooding that you are concerned of? Okay, so the variable is river flow or river levels, river stage. Okay, and this is something that we will also discuss. And we need to assess the hazard related to climate change. So as I mentioned to you, I gave already some examples, fire or flood or other hazard. And but there might be also hazards related to climate change mitigation and adaptation. So if I, for instance, if I choose to adapt by building a dam in order to reduce the vulnerability to floods, a dam reduces the vulnerability to floods if it's well managed. Dam construction means adverse effects on health of people. For instance, on groundwater, river flow. River flow is deprivated, so there is a decrease in ecosystem services which are supportive of healthcare, etc. And vulnerability and exposure are then assessed through the identification of health determinants. This is extremely important to you. So you have to identify what are the determinants of health. Is it temperature alone? Fine. Is it the temperature associated to the concentration of wildlife? We will discuss also about health determinants. I think this is one of the most interesting thing that I learned while preparing these lectures. I didn't know about health determinants before. As I said, I am an engineer, I am an hydrologist. I had some connection with medical doctors, but not really very long time connections. And I found it very interesting because, as we will see, there are several lists proposed by different organizations of health determinants in relation to climate. And then what we need to do is to identify the health benefits which may derive from climate change. And we have to identify, it's not mentioned here or it is mentioned implicitly, what are the negative effects of climate change mitigation and adaptation. And then we have to make a synthesis of the results. Okay, let's try to go into the details. And we refer here, as a premise, to the current usage of the term climate change. The current usage is associated to the meaning of anthropogenic climate change. And I want to discuss first the estimation of hazard change due to climate change. So, as I said, let's assume from now that climate change is anthropogenic. Whatever definition we use, and we discussed already this, you have to be fully aware of the fact that climate is naturally changing. And not only because we have glaciations, but because we had also recently oscillations of climate that we know very well. And for instance, we believe that the decline of the Western Roman Empire was caused by cooling that occurred from 250 to 600 after Christ. And we also know that around the year 1000, there was a climate optimum, which favored the development of civilization in Italy, but then it was followed by the Little Ice Age, which lasted from about the good weather during the medieval age is called the medieval warm period. And in web pages, you can find a link to Wikipedia. It's very interesting. It was a climate optimum, but it was followed by the Little Ice Age. The Little Ice Age lasted from about 1600 to 1750. There was an expansion of glaciers. There was an expansion of areas that were covered by snow. And since 1750, glaciers started to retreat. These are natural oscillations, or at least let's say that these are oscillations that occurred in a period when human emissions of CO2 were very low. And what is interesting to notice here, and this is the reason why I mentioned these natural changes to you, is that historically, the warm period had been associated to favorable conditions for societal development and the health of people. Because there were less floods, during a warm period, people experienced less floods, they experienced more favorable conditions for agriculture, they found good conditions for social expansion. This is interesting. During cold periods, and I mentioned the Roman Empire, for instance, during cold periods, they experienced floods, they experienced economic crisis, which in turn implied an impact on the human health. And this is indeed interesting. It is interesting because it is an experience that we have to take into account. So, a warmer climate means really a negative overall impact on the human health. For some illnesses, for sure, but overall, if we take into account that foodborne diseases may decrease in a warm period, if we take into account that also waterborne diseases may decrease, I mean, overall, it is interesting to take stock from this experience in the past. Actually, I stumbled into a paper that was published by one of my closest colleagues in 2019, I think, and they tried to analyze based on historical witnesses, historical remarks like the documents that were issued were written by the monks in the monasteries. They tried to analyze the frequency of floods in a long period, in about 1,000 years, and they found indeed that they found an increased frequency of floods during the warm periods. On the other hand, they found also an increase of floods during the recent period, which is a global warming period. So they found that this is anomalous. They said, okay, and we found that in the past floods were associated to cold weather, and today it seems that they are associated to warmer weather. So it may indicate something different that is occurring, like a kind of human influence, anthropogenic influence that we cannot really decipher well. Or maybe simply the fact that recent floods are more efficiently reported. And in the past, they may have missed some information. But still, I found also this interesting, because what happened in the past, it's useful for our experience, but on the other hand, in the past, we had less CO2 concentration. So maybe that indeed the present is different.
How does the flood happen during the cold weather during warm weather now?
Why, sorry?
I didn't understand. We said that floods can happen in cold weather.
Yes. What we found is that in the past they had found a correspondence between floods and cold weather on average. Today, it seems that this correspondence is broken. So your question was, how can be a flood originated during cold weather? Because during cold weather, they found that there is an increase of extreme precipitation. So you may say, how can precipitation increase if the weather is cold and the atmosphere is less capable of storing water vapor? I mean, keep into account that what we know of the climate system is an interpretation. So the fact that we know that the atmosphere is indeed able to store more water if it is warmer But is this water entering the atmosphere or not? Because during the warm weather, you have also less evaporation because you don't have water over the ground, because it's more arid. So indeed, there are many mechanisms in climate that we don't know. And so it is, there might be many possible explanations for a more frequent flooding during the cold periods, like for instance the higher probability of rain snow effect or something like that. And most of them we can elaborate in interpretation, but we don't have really an explanation that is very rigorous. So we have to accept. I think in the human model we more or less do the same thing. So there are some reaction of people to treatment that sometimes you cannot really explain, so you don't know everything.
And what about in warm weather? There is an increase.
In warm weather, my interpretation is that in warm weather, you have an increased frequency of flooding small basins. If you look at the floods that are occurring in Italy now, they are over small basins. The Po River, the Arno River. The Arno River, I mean, was a bit concerning last week, but actually didn't give any big problem. The problems were given by small rivers. And as I think I already mentioned this to you, small rivers are put in critical conditions by short-term rainfall, like rainfall that lasts for 1 day or a few hours. Large rivers, they are instead sensitive to long-term rainfall. For the Po River, we need a rain lasting at least 1 week. So my interpretation is that probably in the warm weather, you have an increase of the frequency of what we call flash floods, which in the past probably were not reported, because now we know everything. But if a flash flood occurred in the Middle Age, keep in mind that first the density of population was much lower, so probably they didn't care. And then there is probably the problem that they were not reported, because a large scale flood means that several people are affected, several monasteries maybe, several people saw it, and probably they were more easily reported. I discussed this with my colleague, and he didn't exclude that. He didn't exclude that now we are getting a more efficient reporting. Okay. Now, what are the climatic variables that we may select in order to be indicators of, and they can also become health indicators, health determinants. There are several examples, several lists, and I would like to make a selection. And in my opinion, what we have to consider mainly is temperature, wind, long and short-term rainfall, river flow and groundwater flow, which is related also to rainfall, but I like to keep it distinguished. And okay, let's say other hydrological variables. So basically, these are, in my opinion, the main health determinants. So in a few words, I would say that, but this is very personal, it's a personal interpretation. In a few words, I would say that temperature and water cycle are the determinants. And temperature is relatively easier to predict. Water cycle is a bit of a problem because it's more uncertain. Okay, and temperature, given that you had education on probability, temperature is Gaussian. Variables related to the water cycle are skewed, not Gaussian. And Gaussian means very regular, smoothly varying. And if you think of temperature in time and space, is smoothly varying. It's not up and down, up and down. If you look at rainfall, it's intermittent, very rapidly varying in time and space, so a bit of a problem. The feeling is a bit of a problem to predict them, but the feeling is that temperature and water extremes are increasing under global warming. So let's assume that it's true. It's a feeling that, as I just mentioned to you, is also supported by the Clausius-Clapeyron equation, which says that the atmosphere can store more water vapor with a higher temperature. More water vapor, people think that imply more rainfall. Actually, if we look at long-term rainfall, our data, our observations in general say that there are no significant changes. So keep this in mind. If you look at annual rainfall at the global level, even if you consider the global average, is not significantly changed recently. And recently means after global warming in the past 30 years. There are oscillations, there are up and downs, but overall we can't identify a very much different term. And this is, on the other hand, long-term rainfall. But short-term rainfall, indeed, there is the feeling that it's changed, it's becoming more intense. And there has been a lot of studies on that. But let's suppose that short-term rainfall is increasing. So phenomena that are occurring in a very short time, which are difficult to measure, and for which we don't have many measurements, let's suppose that they are increasing. Okay. You can use climate models, but for temperature they are okay, for water cycle less reliable. You can get simulation from climate models easily. I think I already mentioned this to you. There is the Copernicus Climate Data Store. It's easy. On the other hand, it requires some coding. So it's easy, but not really user-friendly. And what people do usually, given that we have several models, people usually generate ensemble simulation. They want to obtain an envelope of future prediction of temperature, of rainfall, whatever. So you may get, also from the medical point of view, you may get an indication of how the probability of getting an extreme event is changing. And you may assume, for instance, and this is the first very practical guideline that I give to you, that if you get a percentage change of rainfall, you can assume that you have a percentage corresponding percentage change, same percentage change of river flow. So if you have the probability of getting a heavy rainfall that is increased 10%, you may assume that the probability of getting a flood is also increased 10%. So you may make the assumption that the relationship between rainfall and flood is linear, extreme rainfall, and flood is linear. Let's suppose that you get a prediction that says that extreme rainfall is increased 10%, then your risk of flooding is also increased to 10%. This is a rule of thumb. I just want also to give you my personal rule of thumb, what I call the 10-20% rule. Now, our experience, and several experience, very practical one, and several other indications suggest to us that if you have to get a guess of the increased probability of getting an adverse event, this guess is in the order of magnitude of 10-20%. I want to give you another indication. This is something that I realized by myself, because I thought why this kind of indication comes out so frequently. Why many stakeholders, many managers of river networks, why many basin authorities, when I say, look, predictions of hydrological variables are very difficult, why they say, okay, let's assume that we have a 10% increase. Why is that? And then I saw that there are, in other countries, I learned this 2 weeks ago, in several, according to me, several countries in Europe and out of Europe issued guidelines for estimating the hazard of future adverse event after climate change. And they are ranging from plus 10% to plus 50%. The highest one is the Canadian government. They suggest to increase the forcing, to increase the risk of 50%. And this is the highest. So why is that? I think the reason is that what people really see is not a huge increase of like twice of adverse events, like twice, or I heard some people say probability is increased 10 times, like what was first with a chance of 10%, now is like close to 100%. This is not really what people see in practice. People that are working with floods, with what happened, they see an increase of the order of magnitude of 10, 20, 30%. Keep this in mind. Like, if you have to make an estimate of the effect of climate change on an Earth determinant, it is safe to say, okay, let's take a plus 20. But let's try to go into more details now. An important thing is this slide. What are these? These are emission scenarios. And basically, they are prediction of human emissions of CO2. So you see, up to present, this is the trend. And no climate policies. This is what is called business as usual. Business as usual, how they compute it, simply, they take this trend here, and they put it forward into the future. And why an envelope, a huge envelope? Because these are predictions given by prediction models. They are societal models that try to predict our development. And different models give different predictions. So this is why there is the envelope. But there are also more optimistic predictions. And for instance, we are predicting that with current policies that are already in place, we go down to the scenario that you see in orange. They have also some acronyms. I don't remember them now, but you can easily find them. So orange is, they associate here what is the increase of temperature that is predicted by 2100. And by 2100 with respect to pre-industrial levels. So now we are plus 1.2. This is plus 2.7. You may remember that the Paris Agreement is committed to limit the warming to plus 2, back to plus 1.5. And these are the other scenarios, and this is the 1.5 pathways from the Paris Agreement, and this is the 2 degrees pathways from the Paris Agreement as well. So keep in mind that when you get a climate prediction, you have to get information on the scenario. The scenario business as usual is considered too overly pessimistic today. And people are now frequently adopting the current policies, and some people say that we already picked I saw a publication last week. There was a scientist that stated that in his opinion, in their opinion, we have already picked the emission of the concentration of CO2 in the atmosphere. Here it is predicted to peak around 2050, but now there are some measurements that it seems that may deliver a more optimistic prediction. These climate simulations, climate predictions are called climate projections. And I just want to mention to you a study that I recently completed, and then we make the other break. This study basically was focusing on the risk of drought, and we took into account 13 climate models to predict the risk of drought in northern Italy up to 2100. And then we used historical data and made a classical prediction based on historical events. What we found is that the prediction based on historical events is more conservative with respect to the prediction of the climate models. Why? Because there is uncertainty. So the prediction from climate models should deliver, according to our perception, a higher risk with respect to a prediction which is based on the past climate. Actually, what we found for the specific case of the Emilia-Romagna region is that the classic prediction is more conservative. When you find such an outcome, you have always to trust more the classic approach based on information and our experience. When you see a model that gives a convenient result, it may be fine to trust the model. But when the result doesn't convince you, or I'm talking of the model, then it's much better to rely on our consolidated experience. Okay, 10 minutes.
There were these 2 rows that people can stand on, like 2 places. Mini amphitheater kind of range.
Okay. Let's now, we are still focusing on hazard. Let's now focus on an important topic, climate change mitigation and adaptation. What can be the effect of a hazard? And because there are many actions that are possible in order to our main target, reduce our carbon emissions. And here you see a collage that is taken by Wikipedia. Solar farms, electric transportation, plant-based meals, because I'll show you later on a graphical representation of the amount of our emissions, and the emissions related to the production of meat are very, very relevant. And food production, and in particular meat production, are responsible of several emissions. And so these strategies have, on the one hand, a positive effect in terms of emission reduction. On the other hand, they may have some downsides. For instance, solar farms are decreasing infiltration, rainfall infiltration into the ground, which means that less water is stored in the aquifers. And we know that groundwater is an essential resource during drought, especially. Electric transportation, you know, the debate on the displacement of batteries and on the impact of that the electric transportation may have. So it's important to get some indications on this impact, and in particular on those that are called unintended effects. I think it's very significant to refer to a recently published review, which is open access, of health impact studies of climate change. And in particular, this review refers to the negative effect in terms of health of climate change mitigation and adaptation. And let me try to get it on this. Okay, it's not important that I get it on the screen. But the paper is open access. I will show you some graphs, some figures, and if you're interested, this is a reference that is easy to read. and it's important because it's a review. The way they made the study is that is very simple, and it is very frequently used recently. They made a search in Google Scholar, Web of Science, the web repositories of scientific publications, and then they searched for keywords and identified in this way a good amount of articles. If I well remember, is 81 articles focusing, scientific articles, focusing on this effect. So they found that regarding health impacts, 73% of these 81 articles, so 65 articles, found only positive effects of climate change mitigation and adaptation. 5 articles, 6%, found only negative health impacts, and therefore because maybe the strategies failed, and 20% found both impacts, negative and positive. 16%, sorry, as you see in the second bullet point. Health impact were categorized based on the nature of the health outcome, meaning that, for example, a decrease in deaths is considered positive health impact. So positive is increased with the plus sign in terms of positive is a negative impact indeed. It is considered a decrease of health status, while an increase in this, sorry, I don't understand. I think I was, no, a decrease in deaths. I'm sorry for that. So I go back. A decrease in deaths is considered a positive impact, which means an improvement of health, while an increase in disease cases is considered a negative impact. It's important to make it clear because sometimes positive is intended with the plus sign, and the plus sign may imply indeed a decrease of health effect. So it is the definition is important. And in 5 articles, there was uncertainty concerning the direction and magnitude. Okay, and around half of the reported health impacts were related to mortality. And for instance, avoided or excess premature deaths. And over a fifth of articles, so about 21%, reported only morbidity-related impacts, which were quantified using a plethora of indicators, such as disability or disease cases, number of hospitalizations, number of intensive care unit admissions, etc. And about 30% of the article reported both mortality and morbidity. So this is a graph that it's interesting because it lists the health outcome categories, and also you see the number of articles. So these are interesting because they give to you an idea of what this review considered as an health outcome of climate change mitigation and adaptation, but which means climate change. So accident injuries, communicable diseases, food and nutrition related issues, maternal, neonatal and child health, mental health, non-communicable diseases, which are split into respiratory related, diabetes, dementia, CVD, which is cardiovascular disease, and cancer. And then if you go down in the left graph, sexual and reproductive health, soil, water and waste related diseases, vector related diseases, and zoonosis, 0, nothing emerged from the review, and unspecified. Now, what is interesting is, what is even more interesting, here you get a list of the health outcomes on which you may focus on. What is even more interesting is this graph. It is not easy to interpret it, but actually it's it's easy. It doesn't look easy, but it is easy. So this is the hazard change after climate change adaptation measures. So in the left of the figure, you find the measures, the strategies. So critical infrastructure, network and services, meaning that we operate on improving these services in any way. It's an action on these services. And then there is, for instance, if we look at the critical infrastructure, network and services, then you get air conditioning as a case, and you see the percentage in terms of the number of articles that have considered this effect, which may have an effect on air quality. So on the left you have the system. In the light blue column you have the measure categories, if you look in the bottom of the figure, and then the health determinants and the health outcomes. So basically, again, critical infrastructure is the system. The measure category is air conditioning, which has an influence on air quality and also has an influence on air temperature. Of course, the influence on air temperature is supposed to be a positive influence, while air quality is supposed to be a negative influence. And then these are connected to the health outcomes, non-communicable disease and cardiovascular disease, with the percentage that you see in terms of number of cases in the picture given by the article they reviewed. And then system, human health, measure categories, health and health system adaptation. So it means that you may improve the healthcare system. This gives an effect over air temperature and over accident to health services, which has an impact. Air temperature over the connections to unspecified and other diseases, other type of diseases. Other system, other cross-cutting risk, which is connected to climate services, social safety, disaster risk management, which are connected to other health determinants. But let's have a look, and then there is living standards as a system, water security and food security. So the measure categories, let's list them from the top to the bottom: air conditioning, green infrastructure and ecosystem services, albedo increase, including cool roofs, sustainable land use and urban planning, health and health system adaptation, climate services, including early warning systems. Early warning systems are an essential action to reduce vulnerability. And then we have social safety, and then disaster risk management, livelihood diversification, water use efficiency, resource management, and efficient agricultural systems. In terms of health determinants, this is also interesting. Air quality is considered to be a significant health determinant according to this paper, and indeed it is, according also to our understanding. Air temperature, and you see that it's connected to a large proportion of diseases, most of them unspecified, but it's a strong connection. And then capacity of healthcare system, so an essential health indicator. Accident to health services, so it means that it is related to the robustness of these health services, robustness in extreme conditions. Employment income, it's health determinants because, of course, if people have have more capacity to react, have an income that is higher, this implies a higher capacity to react, which means a reduction of vulnerability. There is access to food. This is food security is for sure a very important health determinant, the dietary. We know that dietary is strictly related to health conditions, baseline health conditions, and then it's related to the impact. Access to education, this is also considered to be a health indicator. And housing conditions, water quality, water quantity, access to drinking water, access to sanitation facilities, access to food. And in terms of diseases, health outcome, non-communicable diseases, cardiovascular diseases, unspecified, MNCH, I'm sorry, I don't remember what is, but we can look at the paper, mental health, soil, water, waste related diseases, vector related diseases, and food and nutrition related diseases. This diagram is called, let me check, and because it has a name, it's a diagram that is very useful to connect cause and effect in a quite intelligible way. Of course, what comes out here is it's the Sankey diagram. Now, it is spelled like this. Just 1 second. So I make an experiment, but they turn okay. It's okay. Should be there. It's called Sankey. Okay, and I think that, let me check here, but we don't see it. Yeah, okay, let me see. PC again, but I don't think you see it. I think, okay, so let me just, I want to show you. Okay, so let me stop sharing and share again. And then I take this one. So now you should see, no, it's again that. Just 1 second. Okay. I don't understand why it's, it's correct. PowerPoint, I think, okay, here it is. Good. Just 1 second, I need to. Okay. Almost there. Perfect. So I take this opportunity to see. This is the paper that you should see there. Yeah, it's open access. And it is recent. It's 2023, January, February. It's very recent. In general, the literature that I found is, as I said, it's recent. And let me now show you the figure which we were discussing this one. Sankey diagram. There is a link on the Wikipedia page. And it's a data visualization technique, like a flow diagram, which emphasizes the connections. So the connections between, as I said, causes and effect. It is a simple concept, but anyway, I think it is useful. And then this one, let me just, okay. This one is, but let me go back to the PowerPoint presentation. I think it is better. Okay. Here it is. This is the cycle diagram of climate change mitigation. This is different with respect, of course, to the second one, which referred to adaptation. It's still shared. Yeah, it's still shared. Perfect. So here you see again sectors, measures, health determinants, and health outcome. If we go on the sectors, this is mitigation. So basically, these are sectors where we can work to reduce emissions: building, industry, energy, other, transport, and follow. I don't remember what is, but okay, we can look at the paper later on maybe. Here we are missing. Yeah, I think a follow is related to agriculture, because I was saying we are missing agriculture here. Agriculture is indeed a sector that produces, as I mentioned, a lot of emissions. And so you see that indeed here there are some of the measures which are related to working over agriculture. Just to give you an idea, let me move forward with the presentation a bit. Okay, here it is, the global greenhouse gases emission by sector, and this is given by our working data, is a public domain data. And you see that indeed energy production is playing the role of the lion here, but then the second is agriculture, forestry, and land use. And then industry is just a small bit. And so basically, you see that there is also transport related to energy production, energy, let's say, and agriculture is also split in deforestation, cropland, crop burning, and agricultural soils, rice cultivation, and livestock and manure. Livestock and manure is 6% of the global emission, which is, I mean, it is indeed a good percentage. And here road transport is included into energy, because it considers energy with a wide perspective. So in order to move a vehicle, you need to produce energy by burning fossil fuels, so it is included here. Road transport, you see that the amount is 12%. Aviation, it's only 2%, which doesn't justify really why with over certain types of emissions there is a lot of attention, a lot of effort by people, while it's not really that influential. Aviation is, I mean, 2% is significant, but it's not really that huge amount. Okay, let's go back to this diagram. My suggestion for you is just to have a look here. In order to get what is most interesting to you is the health determinants. Here is air quality again, air temperature, radiation, and noise, physical activity. This is an important health determinant, because with the increasing temperature, it has been proven that people tend to reduce their physical activity, and the physical activity is extremely important. As you know, it's an important health determinant. And then the traffic as an health determinant, and the diet again. And you see the diseases that are related to that. What's also important here to see is that non-communicable diseases are indeed playing a relevant role. Of course, there are many. So the fact that they are non-communicable doesn't imply that they are not significant, because of course they are many, so it is justified that they play a relevant role here. Again, my suggestion is just to look at this diagram, because this is an interesting review, it's very recent, and you can get an idea of the health determinants that are relevant to you. Now, vulnerability and exposure estimation. Health determinant, again, so let's focus on these, because these are the indicators of vulnerability and exposure. Because, of course, once that you determine the health determinant, you can determine, you can estimate the vulnerability to that. So if your health determinant is the relevant health determinant is temperature, of course, we can estimate the vulnerability of people to temperature, and we can estimate also exposure. This is another interesting, I think, point for you. And I found it interesting for me, actually, because it is something that in engineering very often it's not considered, but I found it interesting. And what I found it interesting is that there is a lot of discussion on that. There is a lot of research. What are health determinants? They are features of a given system, which may be a biological system, a sociocultural system, the climate system, the economic system, behavioral systems, and institutional systems that may affect human health. So in a health determinant, you can find a climate variable, but you can find also an economic variable like the public debt. And this is something that is coming to our attention with the increased frequency, the public debt as an indicator of vulnerability to climate change. Because if we don't have resources, if we don't have public resources, how can we adopt a strategy to increase vulnerability to climate change? And the public debt is, of course, debate today. Is affecting the health of the healthcare system. It is affecting it. And you know that in order to find the resources, now the government is forced to reduce the amount of funding to the healthcare, and indeed this is a problem. So how can we identify the health determinant? I found, maybe that you know it already, I found an interesting contribution. It's the Lancet Countdown, tracking progress on health and climate change. Since 2015, so just 8 years, the Lancet Countdown has been providing a global monitoring system that tracks these interactions between climate and health. So I'm sure that I cannot open it directly. Anyway, I have some figures. And so what are the health indicators? And CCHI is an acronym for Climate Change Health Indicator. And they identify 5 domains of the climate health system. And these are the domains, so health hazards, exposure and impacts, adaptation planning and resilience, mitigation actions and health co-benefits, economic and finance, and public and political engagement. And of course, in health hazard, exposure and impacts, you can include the climate indicators. And there is an open access contribution, very recent one, by Di Napoli and others, that presents these indicators and give also suggestion on how they can be predicted. I want to give you an example. This is an health determinant that I took from a recent contribution. It's open access, otherwise I couldn't put it here. Kai et al. 2022. And here it's related to the physical activity. It refers to China. They identified the number of hours of physical activity lost after warming and the progress from 2000 to 2021. On the vertical axis, you see the safe physical activity hours lost per day per person. So it's the physical activity that we may have lost for ourselves every day. There is a baseline that is, the blue line is the average in the period 1980-2005. And then you see the progress from 2000 to 2021. And you see that in this, there is a significant trend. And the map gives to you the spatial distribution of the physical activity lost. And of course, it is higher in the south because in the south, it's higher the sensitivity to temperature. Same contribution here, it gives the health risks associated with climate change in each province in China in 2021 compared with historical baseline average. And here you see a subdivision in groups. And on the left, you have, with the rectangles, you have the all age group. And with the circles, they identify the age after 65 years old. And then there has indicators, the heat wave related mortality in orange, the heat related labor capacity loss in green. This is another problem, a loss of labor capacity. The heat related physical activity lost, exposure to wildfire, exposure to floods, exposure to droughts, and the climate suitability for dengue fever. Not sure why they consider only the dengue here, probably because it is the most significant, it was the most significant for them in their context. The interpretation of these graphs is that basically each graph shows the subdivision into a province, and the span of basically the radius of each component measures the intensity, and the percentage of distribution along the circle means the relative contribution to the total percentage. Now, what is important to notice here is, beside the interpretation, which is tightly related to the context here, so the province of China, I don't think you should focus on the distribution of in each province because, as I say, it's very local. But what's interesting is to take a note, to focus on the health risks. So, for instance, labor loss, loss of physical activity, etc. Okay, let's finish with this slide. So, this contribution by Di Napoli last year and define criteria that must be satisfied by health indicators. And I think it is useful because it helps us to understand what could be the ideal indicator for our needs. First, representativeness. Health indicators should track an aspect of both climate change and health, particularly focusing on the relationship between the two. Relevance. So basically, each indicator should be related to a large population. Robustness, and which means that indeed, if an indicator is used to establish the impact on health, the relationship between that indicator, like for instance temperature, and health should be a robust relationship. Reproducibility, meaning that the way the indicator is computed, the way the indicator is related, the way it relates the climate behavior with the health status should be transparent, calculated using an international agreed and published scientific method, and the timeliness. So the indicator should be computed regularly. Now, what remains to do now is to discuss some example of indicators. I anticipate the next slide: extreme rainfall, droughts, heat waves, windstorms. And these are determinants or indicators, I use them as synonyms, that are climatic, hydrological. If I say droughts, it's an hydrological indicator. But if we include water and the water cycle into the climate system, these are basically related to climate. And next time I will discuss also other interesting references which are listed here. Okay, let me just stop the recording now, because I think that for today we are done. And next week